Well, welcome to the another problem session. So this is the last problem in the IIT JEE 2023 paper 2, and this is a kind of numerical problem you have to do, and you have to write the answer. Enter the answer. You get to 2 decimal places. Okay. Let's look at the problem. So there are 2 questions on this paragraph. So there is question 16, and then it's the same description. I'll go over the description in a minute, and then when you flip it, so there is the end of the question paper. But it's the same description, everything is same, but there's another question that's asked from the same description, and they are not based on like question earlier, so you can think of them as 2 separate questions, but I'm going to just do one video for it because I consider them to be related questions. Okay. This may be the hardest problem for some people, and because the description's a little bit not clear at some point. So this over here is kind of like a heating, some mechanism for heating this container over here, and air is being entered through this entrance at this in this state and over here it gets heated, and right at the corner here, you can see this entire container is at that state. So there is a change of state from this to that, and that's it says that it is maintained at constant temperature 360 K. So this furnace is maintained at that. So this, you might say, this heating happens at constant temperature. So whatever the state here is, this TA is TA and PA, and this is one ideal gas state, and this is another ideal gas state, and okay, so they give all of these dimensions. So this container is quite big. You can see 1 meter by 1 meter. This is very big. That's one thing I got. The air gets heated inside from constant pressure. So you can see this PA is same as PA here. So this over here is a constant pressure, and PA you can say that is atmospheric pressure, but the temperature is different. This TA is outside temperature is given at 300 K, and this temperature is given at 360 K. The hot air with density rho, so the density this is different than the density over here, just at the bottom. So throughout the furnace and throughout this, the density remains rho. Okay. The diameter of this tube is given. As a result, atmospheric pressure, atmospheric air of the density. So rho sub A, when it comes out in outside air. If it's open, then air will come out, and the density outside will becomes just regular air density, which is given. Pressure PA is not given, but you can surmise that it comes out at atmospheric pressure. Assume air as an ideal gas. Neglect the variation in rho and T inside the chimney. So this is the chimney. You can tall, but not so tall that you can say density is varying. You can say the whole thing is a temperature, capital T. Also ignore the viscous effect. Alright, so ideal gas, and assume ideal gas, assume viscous gas. So what's the question that based on this setup? So we're supposed to assume that there's a flow here. So over here is flow is coming from, air is coming in and then is changing to some state, and then it is going to flow through it. Okay, so okay, so redrawn here, so I don't have to write on the question paper. So consider the what we're looking at. So I want to be we're supposed to find the how many gram per second come in out of here. So if we have it's coming out at density rho, solve the rho, and if it's coming with a speed v, say exit. So if I can figure out v exit and this d is given, so the flow rate, mass flow rate will be rho times this area and times this VE, right? So this will be the flow rate. This is the volume flow rate, and multiplied by the density gives me the mass flow rate. So this is we need to figure this out. This already is given. This will be just pi over 4 little d square, and little d is given. So we need to find rho and we need to find VE, and then we will have answered the question. How do I find rho? It says that from this state to this state, this expansion or heating that happens over here, it happens it happens in a constant pressure. So because it's an ideal gas, constant pressure. So if you have an ideal gas, you can say, you probably know PV equals to nRT, but rather than n, because we want to involve density, I want to have mass over molecular weight, RT, right? So this is the ideal gas, but if I put volume down here, then P equals to m over volume over m naught RT. So this is some rho RT over m0. Let's start R over m0, which is constant, time rho times T. So if it's going to go from this state to that state with a constant P, then R over m0 times rho a TA must equal to R over m0 rho T. Of course, R over m0 cancels out, so rho should equal to rho a T over TA over T. So TA is the TA is given to be 300, and this is T is 360, and rho A is 1.2 kilogram over meter cube. So you can write down here, let's say 12 times 10 to the power minus 1, and is 3, and 3, that makes it 10, and 10 times minus 1 is like just 1.0 kilogram over meter cube. All right, so the rho, it's like rho is 1. Just dropping the units, just remembering rho is 1. So we got the rho in maybe 1000 gram over meter cube. How about VE? So VE, how I'm going to get VE? Well, it's the flow, so we just take a point 1 here and point 2 here, and because it's stream flow, we can use the Bernoulli principle, right? So over here, so this rho half rho v square plus p plus rho gh, this combination at 1 equal to this combination at 2. Okay, so but it's actually if you do this, you're going to find out that when it's exiting into coming in density rho but exiting in density rho b. Okay, so we'll have over here we'll assume that v is close to 0 because it's much wider than this. The d is I think is 0.1 meter, and this d is 1 meter. So we just assume that velocity here is 0 compared to the velocity there. So this is 0. Over here is a PA, and you have a rho a gh. This height is 0, so we can have 0. When we go over there, we're going to do you'll see that the potential energy, we have to be very careful. Okay, so half rho v square plus p, pressure there is PA. Then we have a rho g h plus h, but I better subtract the potential energy by just taking this guy out here, right? So this is getting lost by bringing it down here. So minus rho a h plus h. So if I look at it, this gets dropped, and if I convert this, half rho VE square equals to, rho A minus rho times GH plus H, and take this, multiply by 2, divide by rho, and so 2 times 1.2 minus 1 times 10, and this thing is 10 in terms of meter, and this 1.2. So everything has a kilogram and meter units. Let's see what happens. This is 1, 0.2 is 0.2. So this is equals to 2 times 0.2 times 100 over 1 point, no, rho is 1.0. Rho A is 1.2 and rho is 1, so 2, so this is 40. So VE, and this is speed, so I'm going to take positive square root of 40. Positive square root of 40. So we got a VE. So we need to calculate mass flow rate. So rho times A times VE, and rho was turned out to be 1, and A is pi over 4 d square, 0.1 square, and VE is square root of 40. Let me work it out. Okay, so I went ahead and did this calculation, and I want to get it 2 decimal places. So write in scientific notation is 4.96 10 to the power 1 gram per second, because the answer comes out in kilogram, and then I have to convert to gram, get seconds. So that was one of the problems that we have based on this paragraph. Now when you look at the very last part of that paragraph, same paragraph, you don't have to reread this, everything is same, you don't want to waste more time. And over here, the only difference in the question is the tube is now when the chimney is closed, so this will be closed. Instead of moving up, there's nothing going up anymore, so this diagram should be closed. So when it's closed, the question is the pressure develops, right? So let me draw this. So when we have closed this, outside over here is PA, but down here is P prime, not P prime, because it can't escape, so it's going to build up. And it's not, it's still here is PA, rho A, T, A, and over here, so the pressure difference develops between the top and the bottom surface of the cap. If the changes in the temperature and density of the hot air due to discharge flow are negligible, then the value of delta P is this. So all this is still at temperature T and density rho. We can call it temperature T, density rho, and this being, we can consider this an equilibrium. We can talk about same pressure, right? So one way to handle here is, you can see the flow will come and stop. So we can take this as 0.2 and take this as 0.1 and apply the principle again. So this from here to here is, let's call it H prime, which is equal to H plus H. So over here V is 0, over here V is 0, so no kinetic energy in these places. So over here it's going to look like PA plus 0 kinetic energy plus 0 potential energy, and but the density here is different than our density over there, so you'll have a P prime. The density for that density, so this will be the difference, the density difference that will happen between, so rho GH has to be rho GH prime. I'm going to subtract our rho A, which came in, GH. And so we're looking for P prime minus PA. So P prime minus PA, so that's delta P, that's the difference between these two, that equal to rho A minus rho GH prime. So rho A is 1.2 minus 1. Okay, it's kind of interesting. 10 and 10. So this is 0.2 times 100 Pascal, which is 20 Pascal, which is 20 Newton over meter square, and that's, so answer will be 20. Okay, so this was a little kind of a tricky problem, taking care of the how to take care of density difference, you know, when there's a potential energy difference and you have moved different amount of mass. So it's like what's happened is you have a mass that's at some mass is over here and some of the mass has gone over here, so you got to subtract off the excess mass you might include. So the density is supposed to go up, then only the difference in density that you should take into account in terms of potential energy change. Okay, so it's been a pretty interesting week for me. I just did this problem different days. I think in the next series of videos I will do some more advanced physics. Probably thinking of doing a series of lectures on gravity. Okay, hang on. All right, take care. See you in another video. Bye.